Just let me know when we're good.
You can start.
Hey everyone. So first of all, I'm sorry about my throat today. I don't know what happened. I went out the other day to eat some dinner and came back, and 2 days later I'm a frog. So first sick since COVID started, I guess. But I'll do my best here to kind of carry through this. So this is part 2 of what we discussed last time, and the topic's different, but it's still related. It's related to thermodynamics. Last time we talked about heat transfer, which is a big component in thermodynamics, especially in power generation. And we're going to talk about that in the application, which is steam power. But before we get there, we do a little background here. So before we start, I want you to kind of look at this image here. I noticed it's a little bit blurry, but look at those numbers on the left. So in the big number in the middle. So the US consumed in 2019 100.2 quads of energy. Now that's energy on the upstream, energy sources. And we have to use that energy to do something else. 1 quad is 1.055 10 to the 18 joules. That's a big number. What that number actually is in terms of, 1 joule is 1 Newton meter. And trying to figure out what that magnitude of that is, you'll learn that as you get into chemistry and physics and engineering courses. But trust me, it's a gigantic number. So that's the amount of energy we pulled from our environment, whether it was solar, from nuclear reactions, from hydroelectric dams, from wind, geothermal, natural gas, etc. So natural gas, coal, biomass, petroleum, that's the chemical energy stored in there, etc. So that's where energy came from. What did we do with it in the United States? Well, we use it for a lot of different things. The problem, though, is that we also wasted a lot of it. And that's what we're going to be talking about today, is how do we limit that wasted energy? How do we understand the system to pick the right one so we have the least amount of wasted energy? Because look at that picture. Now, there's a lot there. So I'll leave it here for a minute. But I'll talk about it. What you can see is where that energy went through. And the bulk of it, 37% of it went to electricity generation. Electricity generation, you can see, is used for a lot of different things. We've used it for residential, commercial, industrial, transportation, a little bit transportation. But what's really important here is that far right side column there. Of all the energy on the left side that we used or we pulled from our environment, 67.4% of it was wasted. Now that wasted energy is wasted as heat to the environment, whether it's in the exhaust gases, through a condenser and steam power plant, heating up a lake, etc. 33% of it was used for actual usable energy. So whether that was moving a vehicle to the, generating electricity that we were able to use, etc. In the electricity generation part itself, that 37%, you can see that about only 33% of that energy is actually used. The rest of it's all wasted in the process of just making it into electricity. In a steam power plant, you've got wasted heat. In a gas turbine, you've got wasted heat. In a electrical generator, that's, or a diesel generator, you've got wasted heat. So we only actually are able to use about 33% of that. Then down the bottom, you've got the petroleum. A lot of that's for gas. We're not going to really spend, or for transportation, automotive engines. We're not going to look at that too much today. But we are going to look at that top thing, how we generate electricity and how we pick the right one for the job. Because again, we're trying to reduce this wasted energy. One day we may have less than 68% of the energy wasted, but there's limitations to that, which if you go into engineering, especially mechanical engineering, you'll study the first and second laws of thermodynamics at the undergraduate level. And according to the second law of thermodynamics, there's a limit of how much energy we can actually use. The rest of it has to be wasted. It's not quite that much, but it's a lot. I mean, that's a whole bunch of wasted energy that we are trying to limit. So big number, 67.4% of all the energy consumed in the US was wasted. Now, that's similar across the world as well, because the tools that we all use everywhere in the world to generate our power is similar, and to generate, move vehicles, etc., is all very similar sources. So it's a pretty similar number everywhere. Now, the distribution of where the energy comes from, it may vary. It'll vary depending on the country, but the amount we can use is limited. So as an engineer, especially a mechanical engineer, our job a lot of times is to try and find ways to waste less energy. We know we need energy to run our lights, run our ACs, drive our vehicles, buses, transportation, moving goods across the sea, across land. It's just, we need energy. So how do we do it by wasting less? The main thing we can do, and the biggest thing we can do, is we can pick the right tool for the job. Once you pick the right tool to do the job, then you can try and focus on improving that tool. But some tools are better for one thing than they are for another in terms of efficiency, how efficient they are doing the job without wasting any energy. Once we've done that, so we know the job, we know we picked the right tool, then we improve the tool that we've selected. So one example of picking the right tool would be if you are going to cut the grass in a football field, right? You could cut the grass in a football field with a weed whacker, but that's going to take you all day. You're going to waste more energy yourself physically. You need to eat more food. Weed whacker is not designed to run all day like that. By the time you're done, you're probably got to do it again. So it's a very inefficient tool for that job. You might probably use a big old tractor with a bush hog or a cutting tool in the back that would actually cut it much, much quicker. So picking the right tool, then once you have the tool, you can improve it with better efficient engine, better designs, things we'll talk about. So before we can do either of these, like we just mentioned, we have to pick what is the job we're trying to do. That example there was cutting a football field or a soccer. Well, no, if you're overseas, you call football pitches, I guess, right? It's just, football, we call it football and soccer, but over there, football pitches, I guess. But same thing, big old field of grass, right? But we're going to look at something a little more in line with what mechanical engineers do a lot, which is generating electricity. But we'll get there. So what job are we trying to perform? You have to decide what that is. Depending on what industry you get into, you may be focused on one over another. We're trying to power a passenger automobile or a big rig semi-tractor. They're going to require different engine sizes, different engine designs. One will be more efficient for an automobile than a big semi-tractor. You have a small gasoline engine, probably maybe even an Atkinson cycle now, and hybrid for a small passenger automobile, but you probably have a huge diesel engine for a semi-tractor until they become all electric and big electric motors. We just aren't there yet. You try to power a freight train. Well, you're going to need either electric engine or a motor or a giant diesel engine. Small fishing boat or high-speed motorboat, right? What kind of motor are you going to use for that? A small fishing boat, you can have a little outboard motor that maybe is battery powered. A giant high-speed motorboat, you might need 2 or 3 big 400-pound outboard motors or 400 horsepower outboard motors, and they're all going to require different fuels and different designs. You want to generate thrust for a full-size or model airplane? Or are you going to be trying to fly a small crop duster over a field or a fighter jet at supersonic speeds? They all require different engines because different engines will do the job better. Cut grass in a small yard or a large field. If you have a small apartment and a very small backyard, a weed whacker would work just fine. Growing up, I had a buddy who had a very small apartment. His parents didn't, so he lived there. And when we were in middle school and high school, he just used a weed whacker to trim the backyard. My parents had a huge yard and it took all day with a hand push lawnmower, but different tools for the job. Are you trying to generate enough electrical power for one home during outages or enough for entire cities? If you live in an area prone to hurricanes or power outages, you might notice a lot of homes have generators that are attached to the side of their house. They're gasoline or diesel generators. They're not designed to be super duper efficient because you're only going to use it maybe for a few days a year, a few nights a year. But it's important, especially if you have the money for it. People at the oceanfront, when they're oceanfront properties usually do that kind of stuff. Or you're trying to generate power for an entire city. You're not going to have a small steam power plant or nuclear power plant for one house, but you would for an entire city. So again, what job are you trying to perform? What tool do you need? And how do you improve it? Now, if this was, say, an actual class and we were going to be, doing this for weeks on end and doing some calculations, we might pick one of these things as a group and then focus on it. But because it's not, I'm going to pick the answer for you. We're going to generate enough electrical power for an entire city. That's what we're going to talk about. What are the tools commonly used to do that? There are a lot of tools for that, but there are a few that are ideal for that based on their efficiency and the size, that amount of power they can produce for the cost it takes to build them and the space it takes to build them. So after we decided what we want to do, we need to figure out what are the reasonably available options out there. These options change with time, they change with technology. One day it'll probably all be solar and wind. Right now, solar power panels are not highly efficient enough. Wind power, we just need places for that, and we need battery storage so we can actually store this energy during the off season or during the off times of the day when we're not getting the wind or getting the sun. So those are reasonable, but not necessarily the most, but we'll see. So to do that, let's look and see what are the major sources of electrical power generation in the US. So maybe when you're starting a research thing, you're trying to say, okay, what are the reasonable options? This is where you go online and do some research. What are people using? And then you can start to figure out which one you want to focus on. So in the US in 2018, and this is very similar now, it hasn't really changed much at all. This is just the most recent data that came out in 2019. 61% of the power produced in the US is from steam turbines. Now, the fuel source, it could be a nuclear power plant, it could be natural gas or coal. They're all steam power plants using steam turbines. But 61% comes from that. 24% came from gas turbines, gas turbine combustion power plants. They're actually a gas turbine is very power plants. The device is very similar to what you see in a jet engine, but the application in what you're doing with the exhaust gases coming out of the combustion chamber are different, but it's a similar device. Then you have a big drop off. The 7% are hydroelectric dams. Those are great in areas where you have a place you can build a dam, right? But that's limited by, you know, the geographic location. You got to have a lot of water. You got to have a place where you can dam it up and then drop it down so you can get that power produced through the hydroelectric turbines. 7% is wind turbines. 1% solar voltaic systems. And less than 1% are internal combustion engines. So that would be a big, large-scale generator. So a gasoline generator or a diesel generator that you would use maybe for at a construction site. When you're building a construction site, usually you see a big generator because it's portable, very portable, and it doesn't rely on any local grid when you're trying to build something that's not connected to the grid yet. So that would be an application for that. Solar voltaic cells, you probably see those on buildings. You'll see those around. If you live in Virginia Beach, out near Oceana, they have a giant solar panel field right now. I think it's for the military, just so that they can be off the grid if needed. Wind turbines tend to be out to sea or, you know, in fields. Again, these are the reasonable options. You might need to now figure out, well, where am I doing this at? Where's the city? Is there a reasonable hydroelectric, you know, source? Is there great for wind turbines? What do I want to do? It just kind of depends on what your goal is. Well, for us, we're going to look at the top two. We're going to assume that we are not in an area where hydroelectric makes sense, where wind turbine makes sense. Either we're not near any big open fields, we're not near the water, or we're in an area where the city and the population already voted against it. That happens a lot. People who live on the water who have a lot of money tend to not want to have the wind turbines visible. I think that's, you know, whatever. I'm not going to talk about that. But, you know, it depends on where you're at. Solar voltaic, that's great. But if you're trying to power a big city and we don't have the battery technology yet, we're getting there. Tesla's getting it. I mean, we are getting better and better battery technology. And when that happens, we'll probably have a lot more solar and wind power because those, again, are limited by times of days when you can generate it. But if we can store it, that'd be great. So we're just not there yet. But we'll consider this as a current technology, you know, where things are now. It's solar or steam and gas are the main things. So those are the two. Now we got to figure out which one is best suited for us, right? For the job we're trying to do. And you have to look at the pros and cons then. Depending on what it is you need, you may find one is better than the other. Usually you will find that one is better than the other. And to do that, let's just do a quick pros and cons thing. And again, as a mechanical engineering student, you would take Thermo 1 and Thermo 2 most likely. And in Thermo 2, you'll spend a lot of time studying these cycles, these devices, and you'll really learn all the math and the engineering and the chemistry and the physics behind them. But for now, we're just going to kind of look at them. So steam turbines versus gas turbines. Steam turbines, they're big pros. They can use a variety of cheap fuels. All you need to do is boil water in a huge pot, basically. So you can use coal, you can use natural gas, you could use tree limbs if you wanted to. You could use, you know, leftover dried up grass clippings. You need a lot of it, but you could do it. You can use kerosene, whatever you need to burn, you know, whatever you can burn that will generate enough heat to boil water. So you can use a variety of cheap fuels. They're great for very, very large power demands. You can make a steam power plant about as big as you need to. You can have multiple turbines. As long as you can boil the water, you can make the power. So they are great for large demands. Cities generally have a large base load they need. They know they're going to need so many megawatts of power at all times. Well, steam power plants is great for constantly producing that. And they're fairly reliable. This is old technology, been around forever. You got a boiler, you got a turbine. There's a few other components in there we'll talk about, but they're very reliable. Unlikely to go wrong very quickly. Very simple. Some cons though: high initial cost. It costs a lot to build a steam power plant. You need to have a place to store the fuel. You need to have a giant boiler to burn the fuel. You need to have a place for turbine. They're big, they're expensive. You got to have a cooling system. Usually it's got to be, river water somewhere or lake water. So you got to be on the ground, next to a big body of water. Waterfront property is expensive. So if you don't already own the land, you got to buy that land. It's very expensive to, or kick the people out if he's an eminent domain, which hopefully you don't do that. But again, high initial cost. Big one here is it cannot respond quickly to power demand changes. So if a city knows it's going to need, say, I don't know if this number is accurate, but let's throw it out there, 50 megawatts of power at all times. That's great. Steam power plant is great for that. But if you know that, say, you're rolling into July and you're in a hot climate where usually around between maybe 1 and 4 p.m., everyone's cranking their ACs up, especially during a heat wave, well, steam power plant is not ideal to respond to that. You can jack the power up and you can supply that power, but then when people don't need it, it takes a while to bring it back down again. So you're just basically wasting energy unless you can store that energy that's not being used. And then again, until we have good battery technology that's cheap, easy to use, easy to implement, easy to use, easy to create, it's just gonna be wasted energy. So again, we don't want to waste that energy. So they're not really good for that. They're best for the base loads. And then high water demand. So again, you have a giant condenser, and we'll talk about how this device works. Steam power plants don't work without a condenser. Condensers are cheapest to build with water, as water condensers. Cold water to condense the high temperature steam. To do that, you got to be near a lake or somewhere the place that has a lot of water, and it costs a lot of money to do that. So that's the big con. If you're in the middle of a country with no water supply, steam power plants, steam turbines are going to be tricky to make happen. At least not locally, as a pipe power in. So another option is gas turbines. These don't need all that water. These can reach full capacity very quickly. Gas turbines can turn up and down very fast, so they can, they're very agile. You can say they can react to power surges very quickly, because all you're doing is just dumping more fuel at it, burning it, and its exhaust gases are spinning a turbine blade. Easy to do. Which means they can respond quickly to power demands. So if you know that you're going to have a peak or a surge where every day for, say, 6 weeks in the summer, you need to pump up the power output by maybe 20 megawatts for a 2-hour window, you can do that with gas turbines very quickly. No need to worry about how to store it. It's not going to go to waste. You just bam, pull it up. People can keep pulling it off the grid. You're good to go. Cut it off when you don't need it. Unless, if any, water demands, there's no condensers required. Now, what actually happens usually is you have a combination of steam and gas turbines. If you have an environment where you can have a steam turbine, then you're also usually going to have a gas turbine with it as well, because you can use the gas turbine to handle those peaks that the steam power plant couldn't. But again, we won't get into that right now. But there are some cons. Everything has got some cons. Gas turbines have lower overall efficiency. They're just not as efficient. By that efficiency, we mean the amount of energy supplied to it. How much of it are you actually going to be able to deliver to the other end as electricity? For the same amount of energy supplied, a steam turbine will be able to convert more of that to electricity than a gas turbine will. It's just the way they're designed and the efficiency. And we'll talk about those a little bit later. Net output is lower than steam turbines since more power is required to run the compressors. Basically, in a steam turbine, you do need power to run the pumps, to pump the liquid back to the boiler, but you're pumping a liquid. A liquid requires a lot less energy to increase its pressure than it does to increase the pressure of a gas. And in a gas turbine, you're increasing the pressure of air before you mix it with the fuel. So in the end, if you're looking at how much power can I produce and how much power do I need to supply, you need to supply more power to a gas turbine to compress the incoming air, which just means the net power produced, the difference between the power produced and the power required is going to be a lot larger in a steam turbine, and you can get more usable power out of it. So that is a big con with gas turbines. But again, they're great for reacting to power needs, and you don't need any water around it to operate. But another problem, high combustion gas temperatures will lead to overall life reduction on the gas turbine itself. So in a steam power plant, you are running about 620 degrees Celsius max water through that turbine. It also does it at a relatively low RPM, about 2,500 RPMs. That's, I mean, it's a lot, but it's not like it's, you know, extra, you know, it's not a lot of wear and tear on the actual turbine itself. Gas turbines, you've got high temperature exhaust gases, about maybe 1,700 degrees Celsius, rushing through a turbine of material, you know, metal and everything else, and spinning about 70, 80, 90,000 RPM. There's a lot of load going on there. You got a lot of friction, you got a lot of bearings you got to deal with, a lot of high temperatures, which leads to expansion and compression and all kinds of problems. So there's a lot more maintenance required for a gas turbine than there is for a steam turbine. Now, the gas turbines are smaller, so there may be a little less cost in them, but again, there's cons to it, right? So you got to think about that. So what we're going to do is decide on the one we're going to look at. And because I already put this together, we're going to look at steam turbines. We're going to finalize our decisions with that. And once we finalize that, we say, okay, now that I know which one I'm going to pick, let's figure out how it works, and then I can figure out how do I improve it. Because again, you know, there's so many components to these things, and engineers probably going to be stuck on. Your job is to focus on turbines, and you make a career out of turbine efficiency improvements. But again, you got to kind of figure out what that's going to be. So before we improve a power plant or even know how to do it, we have to understand how it works. You know, by a tool, I mean, it could be steam power plant, gas turbine, gasoline engine. It could be anything. A tool, I'm not talking about just a hand shovel. I'm talking about the overall tool to do something with. So after we've actually understood it, and we spent a lot of time in thermodynamics 1 and 2 as an undergraduate, modeling these things as very simple, very ideal cycles without looking at any of the major losses and complexities. But that allows us to get a better understanding of it. So then we can say, okay, well, what parameter will improve its performance? Do I want to operate certain, you know, stages of it at higher pressure, lower pressure, different temperatures? What will improve performance? You spend a lot of time in thermodynamics studying that again. Because once you know how to improve its performance, you know what the performance is, we can try and find ways to improve it. So a key thing here is, according to the second law of thermodynamics, there's a maximum performance that a steam power plant could produce, or gas turbine, etc. What are the parameters that limit that? Well, we don't need to talk about that today. But if you can figure out what your performance is, how close it is to that theoretical maximum, you can decide, is it worth improving it? Maybe you're already very close to that. Maybe it's not. It's the cost effectiveness of improving it that little bit more isn't quite worth the savings. Who knows? It all comes down to you as the engineer and experience. So what we're going to do is we're going to understand it, and then we're going to determine the performance, and then we're going to figure out how we can improve it. And there's an activity on Blackboard, a lab activity, that's going to give you some hands-on with this stuff. So we picked a steam power plant, and we're going to see how we can improve it. In our lab on campus at ODU, we have a steam power plant, very small. The video on Blackboard will go through that. But very basic steam power plant, how they work. We're not going to get into all the modifications and improvements and stuff. But basically, you are boiling water. So a pressure cooker, if you ever can vegetables, is basically a giant pot of water, and you boil it, and you got a little stopper on the top. And that little stopper keeps the water in there at a high pressure. Once the pressure gets to whatever the stopper is designed to keep in there, you have steam coming out. If you were to pull that stopper off the top and let the steam just shoot out, and then put like a little pinwheel in front of it, like a little, the little thing you blow on, and they spin, you could spin that pinwheel. And if you had maybe a little mini electric generator, you could generate a little bit of power, maybe a few milliwatts, whatever it might be. But that's only going to happen, only going to continue until you run out of water. So the pot will empty. Well, steam power plant is the same concept, but instead of letting that pot empty out, you're actually going to route it into a closed loop with several components along that loop. So the first one's a boiler, and it could be boiled with coal, natural gas, even nuclear reactions that would heat the water up. Now you've got this hot water, you boil it, you're going to have a valve that's going to let it leave the valve or leave the boiler at a certain pressure, and we're going to route it into a turbine. So this is basically a very, very advanced pinwheel. You can see down at the bottom, this fellows, they got the steam turbines opened up. basically the steam would enter at one end and expand through the other end. So it would go down the length of that turbine, which is a series of blades. Turbine is example that is so think about a fan. You plug a fan into the wall and it blows air. Electricity is used to run the motor, spin the blades, push the air, and you remain cool, or cools whatever off you need. Well, a turbine is a little bit different. It's similar, but the opposite, where you are now, instead of using electricity to rotate the blade and move the fluid, you're moving the fluid, whatever it may be, past the turbine blades. Well, that causes them to rotate, and then that rotating shaft connected to it all is hooked up to a generator that makes electrical power. So it's just kind of the opposite of a fan right there. But you have to move the air past it, and we do it by routing steam coming out of a turbine or coming out of a boiler through it. So now that steam turbine is going to rotate, and it's going to rotate at relatively high speed, and it's going to be connected into a generator, which is, if you look on this picture here, it's off to the right there, right? So again, in labs and as an engineering student, you'll learn more about these devices, but it's basically a turbine. There's a lot more to this. You can have a lot of turbine stages and multiple turbines. We won't get into all that, but that's how you generate the power. Now, the steam, after it's run past those turbine blades, it's going to have a lot less energy coming out of the other end, but it's still going to be steam. We have to find some way to complete this cycle. So instead of just letting that steam go out to the atmosphere, like we did with the pressure cooker, we condense it through a condenser. And the condenser is just a giant heat exchanger. So this would make use of the material that we talked about last time. You're going to have this still very hot steam, but much lower pressure. So by pressure differences, the steam will enter a steam turbine, industry style, which you might see in industry. A large steam power plant will have an inlet pressure to the turbine about 8 to 12 megapascals. So 8 to 12 megapascals would be 8,000 to 12,000 kilopascals. By the time that steam leaves the turbine, it's down to 15 or even 20 kilopascals. It's way different. So you go from maybe 12,000 kilopascals down to 10 kilopascals through that turbine. So it's very, very low pressure, but still has, still very hot and still steam. We have to get it back to that boiler. So we condense it through a condenser. And that condenser is basically, you're going to have cooling water, maybe from a lake, that's going to go through one side of it. And you're going to have hot steam coming to the other side of it. And that cooling water is going to be temperature differential. And it's going to cause the steam to cool off and condense back to a liquid. That liquid then can then be pumped back into the boiler. So now you're going to have low pressure liquid, maybe 12 kilopascals of pressure. You're going to pump it up to the 10 to 12,000 kilopascal pressure of the boiler so you can boil it again. And the reason we boil the water at such a high pressure, and this comes back to the second law of thermodynamics, if you study that, you'll find out that the higher the pressure that boiler is, the higher the thermal efficiency you can get. We're not going to get into all the details right now, but that is a big characteristic of steam power plants. So that's just a picture of a very large centrifugal pump that will pump that liquid back to the boiler. So as you can see, these things are large scale. I mean, that big pump on the bottom, that's high enough for a person to walk under. I mean, that's tall. Those are giant. And power plants will have multiple pumps. You can see it's going to cost a lot to build that place. And that's a basic schematic of what they look like. So you need a lot of land. Now this is a coal power plant, but it could be anything. If it's a basic coal plant, you need to have the coal, you need to have the river, then you need to have all the components involved. And there's so much fuel used for this stuff. Just kind of this has been many years ago. I was listening to local public radio, and they were talking about the amount of fuel saved by increasing the power plant efficiency by less than 1%. The overall power plant efficiency, we'll talk about those equations in a bit, by less than 1% saved, I think, $1 million a year worth of coal. Tons and tons of train loads of coal. Because again, there's a lot of energy in that coal, but almost 70% of that energy is getting wasted. So imagine if you were to feed a power plant with, 100,000 pounds of coal. You might as well just throw away 70,000 pounds of that coal up front, because the energy is not going to get used to actually produce power. It's going to get wasted. We have to find ways to avoid doing that. So again, that's where this is all going to, because most of that energy is not going down those transmission lines. And then those go into a house and some of that gets wasted as well. So again, so much waste out there that we try to find ways to improve. So that's the basic plant layout, large scale. How do we improve the efficiency and where do those losses, arise? So we got in the combustion chamber, this furnace or nuclear reactor, there's a lot of energy losses there because again, they're not fully insulated. You may not be having 100% combustion. There's losses up front. Heat exchangers are not 100% efficient or 100% effective. Boilers are not either. If you're in a lab or in a power plant and you touch the side of those boilers, they're hot. That heat that you're feeling is wasted energy going out into the room and not going into the water. So again, not going, into the turbine through the steam. So again, wasted heat. Turbines. There's bearings in there. There's friction. There's a lot of things happening when you're rotating shafts and things. So again, you don't have 100% efficiency, 100% energy conversion. The turbine blades themselves may not be designed with the right, geometry to harness as much steam as possible. You want to do that. The generators converting the power. Those are probably the most efficient part in the chain. Those are very efficient, but they're still not 100% efficient. Anytime you touch anything that's operating and you feel any bit of warmth, what you're feeling right there is energy loss. You're feeling the result of an inefficient design, and that heat is just going to the surroundings, and that's not what you want, unless you're trying to use that heat for something. But usually, when you're trying to make power, you don't want to have anything feel hot to the touch because that's evidence of energy loss, inefficient design. There's only so much we can limit, but we try to limit as much as we can. And again, heat exchangers for the condenser side. Again, not going to be 100% efficient. Also, there's pumps required to pump the river water through the system. That takes power. And this is a good spot right here. I got some questions are coming. We're at a good pause spot, so I'm going to sit here and wait for these. I know it kind of went quick there, so let's pause for a bit. And that's a good question. So what would happen if the steam power plant heated a liquid other than water to move the turbine? Nothing would happen. There are cases of that. The reason we use steam power plant or we use water is because water really is cheap. It's non-toxic. It has a high thermal capacity, and the corrosion is very minimal if it's pure water. So if the turbine's designed that way. So there are cases of other fluids, but in general, usually it's water because of its characteristics. Other liquids you have to somehow, usually most of the liquids you'd have to, manufacture, and that is expensive. So that's the main reason we use liquid for this. But if you have the right design turbine, you can, in a right design, system, you could use other fluids if there's a positive to that. Usually it's just not the reason you would do that. I'm going to pause, see if we have any more questions. Okay. And for that question about the different liquids, when you take thermodynamics, usually in semester 1 of thermodynamics, you study how do you determine the properties of substances undergoing phase changes and things, and then you can figure out why water itself is a really ideal fluid for this as well. Because again, the liquid you're using has to be able to undergo phase changes at certain pressures as well for it to operate. So go back to here. And then pumps to bring the water back into boiler pressure. There's losses there as well because pumps are centrifugal devices, friction and rotating, you get friction and things like that. So again, you got to deal with that. So what we're going to do, and piping between the components, right? When you're in a steam power plant, there's a lot of pipes connecting the components, and those pipes are not perfectly insulated. Also, when any fluid flows through a pipe, you generate friction, and that friction is dissipated to the environment as heat. So again, you have heat loss that way as well. So these are all sources of losses. So performance of systems and devices. Performance in general is a simple equation. It's always what are you trying to get out of it over what did you put into it. Desired output over the required input. That's how you define it. Now there's different different words people use for performance. You might call it efficiency. You might call it coefficient of performance. It doesn't really matter. Effectiveness, it doesn't really matter. In the end, it's the desired output. What are you getting out and what did you have to put into it is your performance. Using that, we can define the performance of every one of the components in the chain, and then through experiment, we can calculate what is the performance of each component, and then we can figure out, okay, which one has the smallest performance? That's the one I need to tackle most likely to improve the design of the system the quickest. If you've got 98% combustion efficiency, but you got 17% boiler efficiency, well, the boiler is what you should probably be focusing your energy on, because you're not going to get much better than a 98%. So combustion efficiency, and all these efficiencies, I've got these listed in the order that you would encounter them in a steam power plant from beginning to end. And what we do in the lab when running the equipment in the lab. So the ratio of usable energy. So you got chemical energy in the fuel. How much of that was released in combustion? That's usually pretty high. But the amount of it usually comes from, it's determined by how well you mix the fuel with the oxidizer, usually air. We can usually get 90, 98% of this, with good combustion. That's not about as high as you can get. We are going to, in this, activity we're going to get to, we'll assume about 100%, but that is usually the highest in the chain. We know how to mix fuel and air. We can get that energy released pretty easily. But once you release it, you got to get that to the water in the boiler, and that's the boiler efficiency. How much are we actually able to use to boil the water? Now, if the boiler is really, really well insulated, you can get a lot of it in there. This is pretty much going to be determined by how insulated that boiler is. Nothing is 100% efficient, 100% efficient, insulated, but we can try to get it very insulated. So that's going to be how much we can get into there. This affected by is the components in the system. That's the boiler is where the boiler efficiency comes into play. Then we want to get that heat and deliver it to the turbine and see how much we can get to how much we can deliver as available to run the shafts, the output shaft on a turbine. And that's the thermal efficiency. How much heat was supplied, and then how much was available to work, to deliver work. Now, not all that is going to actually be seen as work on the other end to the generator, but it's available to rotate the output shaft on the turbine. That's affected by a lot of things: the boiler, the pumps, turbines, heat loss in pipes, everything. Because again, once that energy that you supplied to the water in the boiler gets into the water, it's still got to get that hot steam to the turbine through piping, and there's losses along the way. So that will reduce how much you can actually get to the turbine blades. Mechanical efficiency. Once you've got that steam in the turbine and it's being used to rotate the shaft to generate power, how efficiently can you rotate that shaft with that steam? So the shaft work produced by the turbine over the energy delivered by the steam to the turbine. So how much work was given to how much energy was given to the turbine, and how much of that was actually able to rotate the shaft. Okay. So one way you can think about that, I think about it, energy is, energy is everywhere. It's trying to do all kinds of things at once. Think of a room full of wild cats, feral cats. By themselves, they're not going to do anything you want them to do. But if you take that room and you rotate it upside down and make a hole, and you design it just right so the cats all slide down a little chute one by one by one, well, now that's a lot more organized energy release. If you can design a turbine to take that wild energy coming in and route it so it only goes smoothly past these blades rotating them, that is designing the turbine properly to harness the energy, harness that room of wild cats. So again, how will you design the turbine will determine how well how high your mechanical efficiency is. And then that rotating shaft can be used to run the generator, making the electrical efficiency. That's usually the second highest. So usually combustion efficiency is the highest, the electrical efficiency is second highest, mechanical efficiency is third highest, boiler efficiency is fourth highest, thermal efficiency is lowest in the system. You'll study all that as you go through your coursework. So that's affected by the generator that you design. How do you do that? That's more of an electrical engineer thing. And then you got overall efficiency. Overall efficiency is all of the components multiplied together. That's the lowest overall, obviously. So take 98% times 75% times 10%, whatever, all multiplied together is your overall efficiency. In the power plant we have in our lab on campus, the one that we're going to look at in the activity, the one you'll look at in the activity, we've got a overall efficiency, and the number's going to blow you away, is less than 1%. So we've got, say, 44,000 kilojoules of energy is being supplied for every kilogram of propane, to be what we use on the one end. It's a rough number. Less than 1% of that actually gets to the electric, is turned into electricity. The other, like 99.8% of that energy is just wasted into heat. In real life, it's closer to maybe 10 or 12%. But in real life, I mean in a real industrial power plant for a city. But still, we are wasting so much of that energy. So there's ways to improve that. One of them is to have cogeneration plants where instead of just all that heat that was not, you cannot convert to work, you can still use it for other things. For, there are cases, there's a lot of industry applications where you need a lot of thermal energy. Textile mills, textile processing, food processing, chemical processing. All these things take a lot of heat. And cogeneration plants are cases where plants where you generate power and use the wasted heat for other things. But we're not going to look at that right here. So overall efficiency is bad. What we're going to do now is we're going to go to the steam power activity and look at it, and just kind of, you'll be able to do this on your own. But before we do that, any questions about this? I know I went through it kind of quick. I'm sorry, but when I'm feeling sick like I am right now, my brain cuts off and I just zoom through. So I'm going to pause for a minute. And let me see, and let me know if you guys have any questions about that. I'm going to pull up a video in a minute, which is about 6 minutes. Well, actually, no, I'm not, because I haven't tested my audio yet. But we'll get there. You'll be able to watch that on your own. So, steam power lab activity. What we're going to have, I'm going to have a spreadsheet just like last time. Now, this one's a bit trickier. So, in the one last time, there were some equations that we had set up that you could actually use to solve the problem. Those equations are they were a little more complex in that case. In this case, the equations are actually very simple. I gave them to you, and you'll see them in the lab. The problem is the properties of water at different states, so you can have the numbers to put in the equation, are very complex to determine unless you've studied steam tables and understand how to calculate those properties. So we're not going to get into that. I've got actually the software will automatically do that for you. The spreadsheet, I've got it all set up for you, where if you input all of these data values that I give you in these different locations of the spreadsheet, you'll get them from the activity. It will output the results. Correct. So again, what we're going to do is anytime you're reading gauges in a lab and the equipment's running, you get a number off there. So you got a pressure gauge and you read it, and maybe it reads 100 psi. How do you know if that's the right value? Well, you have to calibrate it first. So ideally, you would record the value of that pressure gauge and thermometers. Well, everything is shut off. So those pressure gauges should be reading 0 psi, which is what you read off a gauge at room pressure. Thermometers should be reading whatever the room temperature is. You get those off a well-calibrated barometer and thermometer you find in the lab or in the room. And then when you run the equipment, you can see then, well, if they read exactly what what they should be reading, which is room pressure and temperature, no calibration required. But if they're off by a little bit, you can calculate the calibration. Maybe you got to add or subtract 10 psi or 2 degrees Fahrenheit or what Celsius, whatever, from the gauges at operation. Well, that's what how you correct them in the actual in the lab or in real life, because we're not just going to replace all our gauges every time they're reading off a little bit. It's too expensive. We're just going to figure out what they should be reading. Well, that's all done in the activity. And that's what you'd be doing if you were in the class and in the lab as a student. Once you get all that in there, recording it from the interactive lab, it will then output all the results. And the spreadsheet set up to where it's not going to give you any results till everything is filled. It took a while for me to create that. Feel free to go through the spreadsheet and look at the cells and see how it was put together. But the point is you got to put what it asked you in the cells or it's just not going to work. So you're going to watch the steam plant video, perform the activity, and then put the data in the cells to get the results. That spreadsheet will perform all calculations. There's no graph to plot here because, again, with the conduction one, we had a step one, we did a bunch of different tests, a bunch of different trials. We recorded data at a lot of different locations. We were trying to see how the temperature varies along that, that brass either cylinder as temperature drops or disc as temperature drops. Well, in this case, it's just one result. We're trying to figure out what is the efficiency of this plant. And in the class environment, you'd be getting a better feel for where those losses are, because you could feel the pipes is very hot. You could see that turbine shaking. You know that it's not, very, very well balanced. There's losses there. The boiler's hot. You see steam leaking out. These are all sources of losses that you can then take and really understand where you should focus your energy on improving the performance of the system. And that's what engineers do. They try to improve the performance. Again, calculations are very complex. If you've taken Thermo 1 or Thermo 2 and you're an engineering student, or you're getting ready to do that, well, you can take all this stuff and you can calculate it using exactly what you studied in the classwork. There's nothing different than what you studied. But for most students, most of you probably have not seen this yet. So let's go check it out. To do that, let me change my screen. And I apologize, but I'm starting to break out in sweats here. I am not feeling good today. And I've got a 4-hour class to teach after this, so we're going to see how that day goes. And that class is actually Thermo 2. We're talking about gas turbines in that class, and jet engines and vapor compression cycles. Let's see, so I'm going to close this out. Let me go to screen share. My Blackboard. Let's see. All right. Now, I was notified last time, and I really, really apologize. I don't know what to do. We've been working with ITS. I had about the majority of the students last time were able to access this no problem. I'm going to put that link back in Blackboard. So actually, let me go to chat here and share this link. And so, Sheeta, can you share that link with everybody? Let me confirm that I've got that right link from last time. Let me see real quick here. Should be the same link. Oh, no, I got to go to my presentation from last time. So give me a minute. I just want to confirm I'm sharing the right link. Sheeta, it looks like it's got some weird FLs and percentages. Maybe that's the way it's supposed to be. Not sure that link works. Oh, the link does work. Never mind. Never mind. Yep, that's the link that should work. So give it a shot, everybody. If it doesn't work, let me know in an email. I know I had a few emails from last time about it not working. We're waiting to get everybody emailed because this will be open for a while. Because you can get both activities in here. So we can work with ITS because we've been working with them. They say it should work. It works with some students' browsers, some not with others. So if it doesn't work, just try a different browser. That's the best I can say right now. And then we're trying to figure out what in the world's going on. But I did notice a lot of students last time told me it did work just fine. So once you get there, make available. Why is this not working? Display after. So now this should be available now. What? Edit. Oh, there we go. There we go. Now it's available. So you should be able to see this link here when you go to the Blackboard. Thermo Part 2. In it, we've got the introduction PowerPoints I just went through. Here's the spreadsheet. You should open up. So let me do a stop share to share my entire screen for this one. This spreadsheet, there's a lot going on there. Read up here. You're going to input the calibrated stuff, just go through the steps on the activity, and it'll tell you. Into the green, input during the lab into blue, and then all the results will pop out here. And notice there's a bunch of stuff. Look at that, a bunch of stuff that's actually locked up there, which is good. Bunch of stuff in that cell. That's really meant to just, that formula is just meant so it doesn't give you anything until everything's inputted correctly. And then we'll output all the results down here. The numbers you're going to get off this are very low compared to an actual industry size power plant. Because again, this is small, this is poorly designed, and poorly designed is old. It is poorly designed too. It was built 30 years ago. And it was actually assembled by some students with some components that had just lying around the lab. So it's not at all ideal, but the nice thing about it is it gives students a chance to explore where, where losses are and how the power plants work. This is a nice little video here. 6 minutes, me walking you through the device, showing you all the components. Watch that first. Then go to the activity. And you'll go through the steps, read every step, go through it, and you'll be able to check all the components, read everything. Again, I know this is not, like being in the lab, but we developed this for students who cannot be in the lab, who say we're off campus or didn't live anywhere in the area. If you're on the lab, I'm in this lab with my students, we get this thing up and running. It's hot, it's steamy, there's stuff going everywhere, and we're running around that thing, getting values and recording stuff so we can actually do the experiment and collect the data. So it's a really cool experiment for that. So I highly recommend getting through that. If you're, if Browder doesn't work, let me know. Let's see. So yeah, so I'm not sure how to, let me see. I will do that. Minimize this. I'm going to stop share real quick. Let me pull that link up properly. So give me a second to share it with everybody. I need to go to, I'm going to go to the source where I've got that from, which is over here. 2021. Oh, wrong here. So yeah, I'm going to be sharing that with everybody in a second here. All right, so copy and paste. So I'm not sure, Sheeta, if all panelists and attendees, I think this will work. So in chat, I just sent to all panelists and attendees that Blackboard link that I had last time. Hopefully, that should get you there. And I'm now going to sit here for a little bit and see if there's any questions. I don't want to go through any more right now. Once you get there, it's pretty self-explanatory. Work through it. And I apologize that I'm not feeling good at all today. I'm getting a little lightheaded over here. my arm is sticky and sweat. So I think I might have broke a fever recently. And so I'm going to just sit here to see if there's any questions before we go. We got a few minutes to go. All right. All right. Well, that's fun, everybody, and I will talk to you all later.
Have a good day, and I hope you feel better.
Thank you. I do too. It's be a long afternoon with my next class.